Hello, and welcome back to Complex Differential Geometry. We're finally going to talk about Kähler manifolds, and I've been waiting to do this lecture the whole series. We've been building up to Kähler manifolds through all the 10 lectures, and I've been talking about how all of these 10 lectures are building up to Kähler manifolds. So we're going to start by having a special recap of what all of the lectures contributed so that we could talk about Kähler manifolds. But before we do that, before we do this special recap, let me just write it here, special recap. I would just like to say that this was supposed to be lecture series that uh, we where we took this overall general survey of complex differential geometry, and that still is the ultimate goal. It's just we use the Kähler manifold as the North Star to guide us and give us a point on the horizon to walk toward as a way to ground ourselves while we study a lot of the tools of complex differential geometry. But at the end of the day, it was just an excuse to look at a lot of different structures that you can define in the complex on complex manifolds. And now we get to use a lot of those tools on this manifold to look at a lot of rich structure on this specific kind of manifold. So let's start with lecture one. Lecture one, L1. So in lecture one, we reviewed real differential geometry. And of course, we couldn't have complex differential geometry without the real version, especially because we defined complex manifolds using real manifolds, real diff geo, right? But even more than that, we looked at a lot of tools that and ideas that we were going to be using in complex differential geometry in lecture one, like local to global patching. We patched together the coordinate charts um, to form the atlas, right? And in no small part, we also defined differentiable and smooth manifolds. And we've been using differentiable and smooth manifolds this entire time. So we have been using things from lecture one. And the only reason is that smooth manifolds don't require you to be complex. So that was lecture one. Then in lecture two, we looked at L2 was we defined complex manifolds. Obviously, pivotal in talking about complex differential geometry. You can't really talk about that without complex manifolds. So already we've defined something very, very useful. But also, we talked about the idea of holomorphicity. I don't know if that's a real word, but if it's not, I'm going to make it a word. Holomorphicity. And this is the central idea that ties our manifolds back to the ideas of complex analysis. The requirement for things to be holomorphic is what allows us to use the results that we derive in normal complex analysis onto our manifold. And this is an expression of, at the end of the day, of the CR equations, the Cauchy-Riemann equations. Even as late as the canonical Dolbeault operators, we were calling back to this idea of the CR equations and how we were making the CR equations more generalized to more and more general situations. And number three, so lecture three, we introduced the complex structure, which was a way of encapsulating in a map what it means to be complex. And this obviously allowed us to make the almost complex manifold, which has an importance for other reasons that we're going to come to. But more importantly and more directly, it allowed us to do this decomposition. We did it in terms of V star at that time because V star was what Chern, Chen, and Lam were focusing on because they were focusing on forms, but it's true for any vector space. So on vector spaces. So V O cross C, we showed that V O cross C is isomorphic to V10 plus V01. And so this we called the holomorphic space, holomorphic vector space, and this we called the anti-holomorphic vector space. And without this, we couldn't really have defined PQ decomposition, which was very important in all of our subsequent discussions, right? So this was also very important. Without this, we wouldn't have an almost complex structure J-twiddle. And so then we had lecture 4. In lecture 4, we defined bundles, especially complex and holomorphic bundles. well, we didn't end up defining holomorphic vector bundles in a chronological sense in lecture 4, but later on I added holomorphic vector bundles back to lecture 4. Maybe next time when we do the lecture series again, we can talk about them at their natural point. uh, yeah, vector bundles and their sections and their sections. And that from there we got all the tensor fields, right? And from the tensor fields we got the exterior portion of them, the alternating or the antisymmetric portions of them. And we've been using tensor fields the whole time. I mean, like we have the G metric tensor. We have obviously J twiddle. That was a tensor field. We have lots more tensor fields. Omega is a tensor field, and it's also an exterior form. And so yeah, we've been using even if we won't see it explicitly, like, oh, this is a new kind of vector bundle on Kähler manifolds. Many kinds of vector bundles and many kinds of vector fields are required in the definition of Kähler manifolds, or even to talk about Kähler manifolds. So again, a very important lecture. Number 5. In lecture 5, we looked at yeah, almost complex manifolds. Almost complex manifolds. And this one, you could say it's a little bit less important, but this is what allowed us to define J twiddle and to have this global tensor field that helped us in our analysis. We've been using this J twiddle a lot. Maybe sometimes I'm calling it J, but it's really the integrable version of the almost complex structure, right? Which turned J into a tensor field, which allowed us to do a lot more powerful things with it. So this is the complex structure. The fact that J twiddle is integrable, and we know when it will be integrable, and that integrable J twiddles exist, is partly the reason why complex manifolds exist. Because if this tensor field didn't exist and was not integrable, then we couldn't have a complex structure on our manifolds. And so we looked at how we make J twiddle integrable, and we also saw that almost complex manifolds tell us the minimum conditions for PQ decomposition. So PQ decomposition only requires us to have J as a 1-1 tensor field. It doesn't need to be integrable. I'm going to give myself a little bit more space here, right? And so these are the things that we found. Obviously, the Nienhaus tensor and the integrability, that was all interesting stuff. That was in as a tool to figure all of this stuff out. Of course, we are not directly using almost complex manifolds right now, but the analysis of what makes a complex manifold integrable gave us a bunch of tools that we are now using. And number 6 is in lecture 6 we defined exterior differential forms. And of course, we've been using this the whole time after we defined them in lecture 6, and now it's more obvious why they're so important. So exterior differential forms, just ubiquitous in complex differential geometry, but also like they're natural. These are the natural objects to do complex analysis on manifolds with. They are baked into the ideas of cohomology and the exterior derivatives, which we've been using all throughout, even in the cohomology part. So yeah, lots of important things we started in lecture 6 with exterior differential forms. So I mean, if you don't take away anything else, the complex PQ differential forms are the centerpiece of complex geometry and are widely applicable beyond Kähler manifolds. So that might be the number one takeaway. That was lecture 6, which allowed us to later talk about Dolbeault cohomology. It allowed us to talk about orientations. It allowed us to talk about integrating things on the manifold. Lots of different things were enabled by lecture 6. So then, moving on to the next page, lecture 7. Here we defined orientations, which we needed to define integration. Now, integration is a fundamental operation on differential forms. Differential forms. They're often characterized as um, geometric objects, geometric objects that, to personify them a little bit, that want to be integrated. So, um, in order to understand a lot of text on complex differential geometry and indeed real differential geometry, the integration of differential forms is a must to understand. And in order to define integration in a consistent way, we needed orientations. So that was the obvious thing to do. But then we also used integration to define Stokes' theorem, which was essential in understanding a lot of the cohomological results, right? Cohomology results. And this is in no small part because differential forms have the interpretation geometrically as flows or objects that measure flows. A one form can be thought of as a machine that captures the information of a vector field. So that if you think of that vector field as telling you the directions of a fluid flow over the manifold, then the differential forms capture that information. And so um, the Stokes theorem being the relationship between the fluid flow inside a volume versus on its boundary has much to do, like, is very tightly integrated with the idea of differential forms. And so integration, very important in understanding how we use that flow field in order to understand the cohomology, the analytical obstructions on the uh, surface of the manifold itself, especially when those flow fields could be the flow fields that are formed when you have vectors that point along your coordinate planes. Maybe that flow field needs to have a certain structure in order for your complex structure to be maintained, right? And so that's where integration becomes really important. But also in the future, in the next lecture, we'll see how Hodge theory is also dependent on these integrals of differential forms. And that's where I was saying that to understand a lot of text on complex differential geometry, you're going to need to know how to integrate differential forms. So in the generic sense, they're important. And for our purposes to talk about Kähler manifolds, they're also very important. So that's lecture 7. We added this a lot. Like, this wasn't originally planned, but I realized this was very important. And so we talked about integration in lecture 7. So then we have lecture 8. 8. So lecture 8, we define Dolbeau cohomology. This was one that I was really excited for in the first place because Dolbeau cohomology is cool in and of itself, but we also figured out how to look for global obstructions. That's what it was all about. Global obstructions. Obstructions to what? Obstructions to solving a particular partial differential equation in this case. That was dw equals, d omega equals 0 in the real case, and partial bar omega equals 0 uh, in the complex case, where you assume that there exists alpha such that d alpha equals omega, where omega is the exterior derivative of some higher um, form, right? Yeah, and in this case, it would be there exists alpha such that partial bar of alpha is equal to omega. And so we did that. We looked for these global obstructions. In the complex case, there were analytical obstructions. In the real case, there were topological obstructions. But we also figured out like closed forms, and exact forms. And so the way that this parlayed into what we're going to talk about now is because we're going to talk about Hodge decomposition, and these all rely on these notion of closed forms, exact forms, the exterior derivative operator, and all of these notions of cohomology um, the cohomology groups, these all factor into Hodge decomposition, and Hodge decomposition is kind of fundamental to like the symmetries of the Kähler manifold. Symmetries of the Kähler manifold. Kähler manifold. And right, and so that's lecture 8. And now moving on to lecture 9. So lecture 9 was about connections, curvature, and Chern classes. Chern classes are very directly required in talking about Kähler manifolds and their symmetries, and specifically Calabi-Yau manifolds, especially the first Chern class. So these are very directly relevant. One way to see the importance of connections is that we need a connection to define a curvature, and then we need a curvature to define a Chern class. But even before that, connections are um, important because we wanted to define the Chern connection, which would be important to Kähler manifolds. We would also, in order to define the Chern connection, we would need it to be a Hermitian connection, for which we would need a Hermitian metric, which kind of gets us to why we did lecture 10 a little bit. We would also need to talk about Levi-Civita connections, and we needed to talk about the curvature form being 1-1 form if for this Chern connection. And then obviously we use the curvature form to define the Chern class. And the Chern class was to do with the twisting of the vector bundle, and gave us a strong topological invariant. Now, in fact, lecture 9 and 10 kind of form like a different branch of that stems from lecture 4. So we went down the path of like lecture 4 to 5. We established the almost complex manifold, and then with 6, 7, 8, we were kind of doing this other branch, or where we were walking down this other branch of exterior differential forms. We were done with that once we talked about Dolbeau cohomology, and then with lecture 9 and 10, we were developing the part that were to do with the Riemannian manifolds and the metrics and all of that kind of stuff that we did last time. And connections and curvature and Chern classes are there independently, but they also develop into these Riemannian manifolds. And so we had to talk about these before we talked about Riemannian manifolds. And Riemannian manifolds are important to Kähler manifolds because they are Riemannian manifolds. So that dovetails us into lecture 10, which is very closely related to lecture 9. With lecture 10, we talked about obviously Riemannian metrics, Hermitian metrics, and we talked about the Chern connection, and all of these are integral to defining and talking about the Kähler manifold. Important to Kähler manifolds. So that's how that's a brief rundown of everything we've done so far and how it's kind of connected back to Kähler manifolds. There's only one structure that's left, one structure that we haven't talked about, and I thought that it developed so late into the process of defining a Kähler manifold is that once you impose the condition on a Hermitian manifold, right? So we also defined Hermitian manifolds, right, in lecture 10. Hermitian manifolds. So that's what we have so far. In some sense, it's the most complicated kind of complex manifold that we've made so far, there's something that we can add to a Hermitian manifold that turns it into a Kähler manifold. It's called the Kähler condition. And we're going to the next thing we're going to do is we're going to look at the Kähler condition, and that's going to turn it into a Kähler manifold. And this last structure really emerges once the Kähler condition gets put into place. So far, a Hermitian manifold is both a Riemannian manifold. That's why Kähler manifolds are Riemannian. But it's also a complex manifold, right? That's what we've been working with so far. But with the Kähler condition, we're going to get this third kind of manifold called the symplectic manifold. And that's what we're going to talk about next. Symplectic manifold. And once we discuss what a symplectic manifold is, we'll be set up to analyze a Kähler manifold. All right, so moving on to the next page, let's talk about symplectic manifolds. Symplectic manifolds. And so what makes a symplectic manifold symmetric? Well, let's start by defining one. So to begin with, let M be a real smooth manifold. We don't need it to be complex to have a symplectic structure. Real smooth manifold. And so how do we turn this real smooth manifold into a symplectic manifold? Well, we need a certain tensor field. Omega is a 0-2 tensor field, and it needs to have certain properties. So omega is a map, obviously, from two copies of the tangent bundle, Tm, to R, or C infinity M R, and it needs to satisfy these three properties. One, it needs to be antisymmetric, so it needs to be a form, or an exterior form in this case. Antisymmetric, so omega xy needs to equal to minus omega yx. Two, it needs to be non-degenerate. This means that if omega xy is equal to 0, then either the vector field x is equal to 0 or the vector field y is equal to 0. A non-degenerate form cannot give you 0 for two non-zero vector fields. That's what it means to be non-degenerate. And number 3, which is the most interesting of the three, is that this tensor field, omega, has to be closed. Let me write it like this. Closed. D omega equals 0. And if all of this is true, then omega is called a symplectic form. It is called a symplectic form. And if M admits a symplectic form, then it's a symplectic manifold. I mean, this is the pattern that we've seen with many things. We introduce a new structure onto a manifold. If the manifold allows that structure to be defined, then it is a manifold with the same name as that structure. So in this case, that's a symplectic manifold. Now, one interesting thing that you might note is that for a Hermitian manifold, we already had the Kähler form, omega xy, right? We even named it the same thing. So omega xy, we defined it as the imaginary part of h of xy, or the negative of it, plus minus, it doesn't matter. And we showed that then that would mean that omega xy is equal to g of j of x y, which means that it needed to be non-degenerate since g is non-degenerate. And we also showed that it was antisymmetric. Omega xy is equal to minus omega yx. So the only thing that would be left for omega to be a symplectic form is for d omega to be equal to 0. And this is exactly the Kähler condition, or it's a Kähler condition, as we'll get to in a little bit. This is called the Kähler condition. If we impose this condition, then the Hermitian manifold gains a third structure. It gains the symplectic structure. So our Hermitian manifold becomes a symplectic manifold. So that's why we can say that a Kähler manifold is a symplectic manifold, a Riemannian manifold, because it has a Riemannian metric G, Riemannian manifold, and a complex manifold, because it has an integrable complex structure, or almost complex structure. So this is because it has an integrable J twiddle, it has a metric G, and now it has a valid omega. So with these three structures, it then becomes a Kähler manifold. So that's what I was meaning when I said that the symplectic structure emerges at the last moment. It's the imposition of that final condition that turns it into a Kähler manifold and simultaneously turns it into a symplectic manifold. So now we're going to look a little bit into what this symplectic structure means geometrically for the Kähler manifold. One thing before we leave this section though is last time I called omega on the Hermitian manifold the Kähler form, and it's not exactly the Kähler form. A lot of people will call it the Kähler form. On a Hermitian manifold that is not a Kähler manifold, omega is not called the Kähler form, it's called the fundamental form. With the editing of lecture 10, I don't know if in the final take I left the name of the form being the fundamental form in there or not, but alongside the Kähler form, but it's definitely not called the Kähler form. It's only called the Kähler form once the Kähler condition is true, and then we call the fundamental form of the Hermitian metric or of the Hermitian manifold the Kähler form. So that's a crucial distinction to make. On a non-Kähler Hermitian manifold, omega is not called the Kähler form. It's only called the Kähler form once we turn it into a symplectic manifold. Hope that clarifies things. So now we're going to move on to talking about the symplectic form and what it means geometrically and what kind of structure it gives the Kähler manifold and symplectic manifolds in general. All right, so let's move on to interpreting the symplectic forms. Let me write that down. Interpreting symplectic forms. So symplectic forms define, they're fundamentally about preservation of area. So symplectic forms are about area preservation. And we're going to see this in the next few things that I'm going to explain. Keep this in mind, that symplectic forms are about area preservation. So using a symplectic form, omega, we can define something called a symplectic area on a symplectic manifold. So let's define that. Symplectic area. So we need M to be an oriented symplectic manifold, since we need access to the symplectic form. And if we have this, then we can define a map A that takes a surface sigma. So sigma is a 2D surface. And here we're not doing anything where we're taking generalizations of 2D surfaces. This is literally a 2D surface, just because we're talking about specifically areas, and symplectic manifolds are deeply intertwined with the idea of area measurement and area preservation in specific. And so if we have higher dimensional symplectic manifolds, the way that they generalize is that they look at different planes, different 2D planes, and preserve their individual areas separately. So let's say that A is a map that takes a 2D surface sigma, and it we define it as the integral. That's why we need this manifold to be oriented. And so if we define it as the integral over sigma of omega, and this is the oriented area, so this is an oriented area, meaning it could be positive or negative. Yeah, so we call this the symplectic area. Now, what is this? Does this have to do with area preservation? What do we find from this symplectic area? What we find is, well, let's think of this situation where we have this curve. I'm drawing it as a dotted line, and let me use some colors to distinguish them. Let's say that I have this surface over here, right? And its boundary is this dotted line. And then let's say that, let me pick a different color, something easy on the eyes. So then I have this surface over here, and it has the same boundary, right? This dotted line. So let's call this a blue plus pink surface. We'll call it N. Or we'll call the interior of it N, which is a 3D volume. 3D volume. And we'll call the surface, the blue plus pink surface, we'll call it partial N, or the boundary of N, right? And so if we call this one sigma 1, then we can call this one sigma 2. And you can think of this as a submanifold of some bigger manifold that it's embedded in, so that N is a subset of M, right? So what happens in this situation? Let's think about the symplectic areas of the blue surface and the pink surface. So if I say that A of partial N is equal to the integral over partial N of omega, right? And so, but we know by Stokes' theorem, so Stokes, again, Stokes coming in handy. So this will be equal to the integral on the interior of the exterior derivative of omega. But remember, omega is the symplectic form, and its exterior derivative is 0 because it's a closed form. So this is 0. This is going to be interesting because if we decompose partial n is, or boundary of n, is sigma 1 minus sigma 2, right? This is not set difference. This is some surface integral notation. So what we're saying is we take sigma 1's boundary and then we subtract sigma 2's boundary, right? Which is 0, right? That's 0 because they have the same boundary. So let's decompose this. So, or integral with respect to the boundary of n of omega is the integral over sigma 1 minus the integral over sigma 2, or the integral over sigma 1 minus sigma 2 of omega, which is tantamount to saying that there is, right, I think I misspoke a little bit. What I meant is that the boundary of sigma 1 and the boundary of sigma 2 cancel out, but obviously I'm getting lost in the sauce a little bit here. So it's this surface, that's sigma 1, and then there's this surface, that's sigma 2, but we're going to assume that they're oppositely oriented to each other. And so their boundaries will cancel out, and then we'll just have the two surfaces, which will constitute the entirety of the surface of n, right? Or the boundary of n. So that's what we get. So this is this whole surface here. And so if we decompose that, we can decompose that like this. It's one integral over sigma 1 omega minus another integral over sigma 2 omega. And since we know that this is equal to 0, then we know that, okay, well, this is equal to 0, and therefore sigma 1, the integral over sigma 1 of omega is equal to the we're just swapping sides, right? So they must be equal to each other. But remember, this is exactly a symplectic area, right? And so that implies that the area of sigma 1 is equal to the area of sigma 2. Remind yourself that all we really assumed is that these are two areas. In essence, all we're assuming is that these are two areas with coincident boundaries, right? In our symplectic manifold M. The M is the symplectic manifold here. Symplectic manifold. So what does this mean? That means that on a symplectic manifold, if two areas have the same boundary, then their areas must be equal. Must be equal. So this is the property of a symplectic manifold. This is the symplectic property. And that's why this is the specific sense in which we are preserving areas. We are preserving areas for surfaces that have coincident boundaries. Symplectic property. Now, we would be remiss to not talk about an interesting result in symplectic manifolds called Darboux's theorem. Darboux's theorem. So Darboux's theorem says that if we have a symplectic manifold, if M omega is a symplectic manifold, then of dimension 2n and admits a local coordinate x1 dot 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 xn comma y1 comma dot 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 yn, then omega takes the canonical form omega in these local coordinates dx1 wedge dot 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 wedge, or sorry, dx1 wedge dy1 wedge dot 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 wedge dxn wedge dyn. And this is always possible, and because of this, all symplectic manifolds are locally equivalent. Equivalent. This is pretty important. All symplectic manifolds are locally equivalent. Their only differences are in their global topological structure. Because the symplectic form, it takes the same form in every local coordinate, that's why this is true. That's why symplectic manifolds are all locally equivalent. Now that we've talked about symplectic manifolds and symplectic areas, we can finally move on to Kähler manifolds. And when we were talking about the symplectic form, we already talked about one of the ways in which we can define a Kähler manifold. Kähler manifold. So let's kind of state that first of all. A Hermitian manifold, M with a metric H and a complex structure J, where the metric hxy, it's a sesquilinear form, is equal to this induced Riemannian metric g of xy, and then up to a convention plus minus I of omega xy, right? And this omega is called the fundamental form, as we established earlier, if omega is closed, d omega equals 0, then M, now let me put an if here, if this, then M is a Kähler manifold, right? So that's what we said. And if M is a Kähler manifold, then it has now three structures. It has a Riemannian structure, Riemannian, because it has a metric G. It has a complex structure due to its integrable almost complex structure J, and and it now has a symplectic structure because it has a non-degenerate uh, antisymmetric 0-2 tensor that is now closed. So there's an interesting thing that you can determine from the Kähler manifold, and this might be my physicist brain working here, but it's interesting to note that the Kähler manifold is the perfect place to unite the three different regimes that are fundamental to physics right now, which is um, general relativity for Riemannian manifolds because they have metrics, and with the metrics you have isometries, and this captures the time-space transformations. You have general relativity that is captured by a Riemannian manifold. You have the complex structure J and it's the compatibility with the complex structure J, and especially the Hermitian inner product that we defined is the inner product on the Hilbert space. So this gives us a link to quantum mechanics, which requires fundamentally complex numbers, quantum mechanics. And lastly, symplectic forms have everything to do with classical mechanics, and this is because the phase space of classical mechanics is this momentum position space, and its main property is that the areas in this PQ diagram, right? This is Q, this is P. Q is position, P is momentum. The areas here must be preserved for Hamiltonian flow, is what it's called. And so that area preservation links us to symplectic manifolds, right? And that's why they can be modeled by symplectic manifolds. And so Kähler manifolds, I don't know if this is the reason why Kähler manifolds are so prevalent in higher level physics, but we're always looking for a manifold to do our physics on, and Kähler manifolds are a candidate for a manifold on which all three of these might be compatible. And so that's why they're very interesting in physics. Of course, we're doing math, but for the mathematician, what's interesting about Kähler manifolds is that are the manifold where these three structures can exactly coincide, right? Because we looked at that Hermitian metrics, Hermitian, always call them Hermitian metrics. We saw that Hermitian manifolds are the minimum set of requirements for a Riemannian manifold to coexist with a complex manifold. And now that we've introduced the Kähler condition, which is the Kähler condition, that was the minimal extra condition that would also make it a symplectic manifold. So for the mathematician, what's interesting about a Kähler manifold is that it's the minimal set of requirements for these three structures to coexist with each other, which is a very interesting differential geometric structure, especially complex differential geometric structure. And so this is why we care about Kähler manifolds in a way. And but what's more interesting is that this is not the only formulation of the Kähler condition, and there are three more equivalent ways to say that something is a Kähler manifold, and therefore it might be interesting for us to look through the other ways, and finally we will look at how they're equivalent. And also, while we list out the definitions of the Kähler manifold, we'll look at the immediate consequences that are more apparent from each of the different definitions of the Kähler manifold. So let's move on to definition number 2. So definition number 2 of a Kähler manifold is, we again start with a Hermitian manifold. So let M be a Hermitian manifold. Hermitian manifold. M, J, H. And so it has, because of its Riemannian metric, it has a Levi-Civita connection, which I'm going to call nabla LC. I'm putting it in the superscript because otherwise we'll conflict with the covariant derivative. So the Levi-Civita connection, Levi-Civita. And so this Hermitian manifold M will be Kähler if nabla LC of J is equal to 0. And what this basically means is that the Levi-Civita connection is compatible with the complex structure. That makes sense, right? Because the Levi-Civita connection comes from the Riemannian metric, and we want the Riemannian metric to be compatible with the complex structure. And so this also gives us a Kähler manifold. So then this will make M, this implies that M is Kähler. So moving on to the next page. Before we get to the third formulation of a Kähler manifold, let's think about what this means for us. And in order to talk about this consequence of this definition, we're going to have to backtrack a little bit and talk about parallel transport. I originally had parallel transport planned for lecture 10, and then I cut it because I thought this isn't leading anywhere and it's taking too long to define. But it seems like we're going to need it in order to talk about this consequence on the Kähler manifold. And the consequence is that because of definition number 2, we find that the holonomy of M is equal to the unitary group of order M. What is the holonomy on M? Well, in order to understand that, we're going to need to know what parallel transport is and use that to define holonomy. So let's rewind a little bit to lecture 10 and let me introduce parallel transport and holonomy. So parallel, and then we will give a short proof for this statement. Parallel transport and holonomy. So we were talking about in connections and curvature that one of the ways in which we can figure out the curvature of a surface is if we move a vector around in a loop. That's what holonomy is. Moving a vector in a loop and noting its difference or noting its change. If it's changed, it has a holonomy. And in order to move that vector around in a loop, we need a way to transport it. And in order to make sure that the vector isn't changing because of something we did, we need to define some way in which the transport is parallel due to our actions. So then the only reason that it could change would be because the surface itself is curved, and thereby it would detect the curvature of the surface. So let's define parallel transport. But in order to do that, we need to figure out how to capture the change in a vector along a curve as opposed to the change of a vector over a vector field as we had before. So let M nabla be a manifold with a connection. So we're talking about parallel transport here. So we're starting off with M and nabla, which is our manifold with a connection. Think of there being a curve. We'll need a curve, right? Here's our parametric curve. It takes the closed interval from 0 to 1 to a set of points on M, and it has to be smooth. Is a smooth curve. So the assignment needs to be smooth. So then, if we want to transport a vector field x along gamma, our parametric curve, then the covariant derivative along gamma. So this is a sub definition that we're going to need, is a unique operator nabla gamma. That's what it's called, nabla gamma. And it has to satisfies three properties. Number one, it needs to be local. If x tilde is the restriction of x to gamma, so like think of x being a vector field on the entire manifold, and if we restrict ourselves to just the vector field along the curve, then that's what x tilde is. Then nabla gamma of x is equal to nabla gamma prime of t, which this is a vector field, right, of x tilde. So Number two, in local coordinates, uh, if gamma of t is equal to x1 of t dot 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 x n of t, where n is the dimension of the manifold, and if x of t is equal to uh, xi of t, that's the coefficient, and the coordinate vectors, partial partial xi, or let's call them j, so that we don't to stick to our prescribed rules. So then the coordinate expansion should look like this: nabla gamma of x is equal to dxk dt plus the connection form omega alpha beta of gamma prime of t. Remember, it's a vector field, so it can go in the slot for the connection form, multiplied by x beta dxj dt. Oh, this should be k. Sorry, this is a mistake in my notes. So dxk dt multiplied by partial partial xk, right? Because at the end of the day, what we want is, so this is the coefficient, and this is the basis vector, or the basis vector field in this case, right? Um, and so this is the expression in local coordinates. Now, if you've seen the geodesics, if you looked into them, this expression should look very familiar. Number three, and of course, if you replace the connection form as we described earlier with the Christoffel symbols, then you would exactly get the geodesic equation. So then it needs to have linearity and Leibniz rule. I'm not going to explain or write this out. I think it's pretty self-explanatory, and if it's not, you can read it in the notes. But linearity and Leibniz needs to be true. Leibniz rule needs to hold. If these are all true, then this is that this is called the covariant derivative along gamma. And basically, if all of this was a little bit too abstract, what we're really trying to say, let me put a box around this. If we, what we're trying to say in this box is the covariant derivative around gamma is an operator that acts like the restriction of the covariant derivative on gamma itself, by which we can assign a vector at the starting point and then figure out how it changes along that curve gamma. And this is how we would do that. These are the properties that we would require for it to act in the way we want it. So now the overall thing that we wanted to define is parallel transport. So how do we define parallel transport? It's quite simple at this point. So parallel transport happens when, so we still have M and nabla. That's our manifold with a connection on it. Doesn't need to be Riemannian, just needs to have a connection defined. And we also have our curve, which is a smooth curve from 0 to 1 to M. And then we say that this transport is parallel if we have X is our vector field. So transport is parallel if, and I think maybe you could guess now what it would be, nabla of gamma is of x has to equal 0. For all t element of 0 to 1, that's the input to the curve. So along the entire curve, if the covariant derivative with respect to the curve of the vector field is 0, then x is the representation of a vector being moved, right? So like, let's say, let me visualize this to make it more clear. We have this curve gamma, right? And we have a vector field that's defined everywhere, including outside of this submanifold gamma. So if it's going to have these vectors assigned along the curve too. So let me put that in a different color. Let's do green. So these are the vectors assigned that are restricted to gamma. So this is x tilde, right? So x tilde is a representation of parallel transport. Like it is capturing the idea of the vector being parallelly transported. This one, let's call that x tilde naught. It's being parallelly transported if for this vector field, this one x, that this is true, right? If this is true, then that restriction of the vector field is a representation of its parallel transport, and it's assigning a vector at each point that represents the vector as it's being parallelly transported along the curve. So this is what we call parallel transport, and so holonomy is one final step from here. It is when we take, so we would call this p gamma, and it goes from t gamma 0 of m. So that's the initial, that's this guy, gamma 0, and to t, or it's not that guy, sorry. Gamma 0 is this point here. That's gamma 0, and that's gamma 1, right? So what we're saying is it's going from the tangent space here in the initial point to the tangent space here in the final point, t gamma 1 of m. And so this is telling you how we parallelly transport. And so we can call this P, and we can call this Q. So this is a parallel transport from P to Q. If this is a round trip, if gamma 1 is equal to gamma 0, then we have a loop, right? Then it's a loop. And that loop is what we use to define a holonomy. That's what we said a holonomy was, right? We said that we needed to parallel transport a vector in a loop. And so we define parallel transport, we close the curve in on itself, and so basically we did this. We made it so that this pink curve looped back on itself so that gamma 0 is equal to gamma 1. And then if we think about the vectors that are along this curve, then if we're transporting this is a holonomy. And so we can form a group from these from all of these operations of p gamma, right? So if this is this, then we would call the holonomy operator, I'm going to call them O of gamma. It's a cheeky name because O is a loop. So O of gamma goes from t gamma 0 of m to t gamma 0 of m, but not necessarily the same vector in both of the tangent spaces, right? The input vector might be different from the output vector, and that's what would tell you that there is a curvature on the space, right? And so this is a holonomy element. Holonomy element. Element of what? Element of the holonomy group. Holonomy element. And so the group of all of these operators is called the holonomy group. So we call that hol p of m nabla because it depends on the connection, right? It depends on how you're transporting. What you've defined your parallel transport to be with respect to the connection is equal to all of these O gamma element. These are elements of GL of TPM, the general linear group, such that gamma is 0 to 1 to m. It is a parametric curve, and also that gamma of 0 is equal to p and gamma of 1 is equal to p, so that it's a closed curve. And that's it. So if, and obviously the signature of that function has to look like this, or that map has to look like this. So then this is the holonomy group of at p, and that is what we call a holonomy. So let's reiterate what the result we got was. It's that the holonomy on m is equal to the unitary group of order m. And so the next thing we're going to do is we're going to prove that this is true using these definitions. That's why we needed to elaborate on all of this. But before we do that, I should explain that what's the relationship between this hol p that has a point on it and hol m. Well, basically what we're doing is let me erase that arrow. Hol m is isomorphic to hol p m nabla modded or quotiented by this group Hall P0, which I'm just going to describe this. I don't think it's extremely necessary to get too much into it. This is the group of operators of contractible loops, meaning loops that can be shrunk to a single point without any obstructions. In order to get into exactly what an obstruction is would take us a long time, but just know for now that these are those loops that can be shrunk to a point. And so what we're doing is we're kind of removing the dependence on this base point, we call it, of the loop. And so Hall M is the group that you get once you remove the dependence on the point, which I guess that kind of is reflected in the notation. In order to be a full explanation, let me also just kind of explain this. This is the rotation group for complex spaces, which preserves the complex length of vectors. So basically what it's saying is that holonomy will only rotate vectors and it will not change their length. So let's now prove our statement. So the statement is or proposition. Let's call it a proposition. On a Kähler manifold, Hall M, well, on a Kähler manifold, M, I suppose, is what you want to say. Hall M is equal to the unitary group on M elements. So this is it. So our Kähler manifold is a 4-tuple, or a quadruple if you prefer, M, J, G, and omega. The manifold plus its 3 structures. And so, well, M is already assumed to be a smooth manifold, obviously. Technically, I should also put in the atlas, the smooth atlas. Anywho, these are the important things that we're worried about right now. So what is the proof? So the proof will come from the fact that, first of all, let's start the proof. Let gamma be a curve, a smooth curve. And so from the definition that we're using definition 2 of the Kähler manifold, right? Which means that nabla LC of J is equal to 0. So let's expand this out. If we restrict this, then we get nabla gamma. We're restricting it to the curve, nabla gamma of J of S, where S is a vector field, is equal to J of nabla gamma of S, right? That's what it means. And so, but if gamma is a curve, then that means that P gamma after J is equal to J after P gamma. So they commute. P gamma and J commute. That's what this equation is telling us, right? Because all we need is a gamma for which nabla gamma is equal to 0, right? And then we would have a parallel transport, which is how we made this implication. I hope that's clear here. So we know. So if we take P gamma to have gamma 0 equals gamma 1, as we said before, then we get a member of the holonomy group, so O gamma, and then we get the holonomy around P. So then that implies, so then from here we get O gamma after J is equal to J after O gamma. So they commute. So O gamma and J commute, because O gamma is a subset of P gamma for where P and Q are equal. This means that because these commute, that means that the idea of commuting with J is essentially to say that something is complex linear, because J essentially is the same as multiplying by I. So if you commute with a multiplication by I and you're already a real linear operator, then you're now a complex linear operator. So now O gamma is an element of GLMC, the general linear group of order M over the field of complex numbers. So we've established that O gamma respects the complex number transformations. So now what we require is to look at the other side of it, which is that because nabla LC of G is equal to 0, this is a property right? Metric compatibility is a property of the Levi-Civita connection. So property of the LC connection. We can translate this to G of O of gamma X O of gamma Y is equal to, so this is another kind of compatibility. It's the compatibility between the metric and the holonomy operator, G of X, Y, right? And so this means that so the holonomy has to respect the group of isometries on the Riemannian manifold, and that is going to be the orthogonal group on 2M, right? So that's the real version of UM. But since okay, so that O gamma has to be an element of this in order for this compatibility to be true, right? So then if O of gamma has to be an element of the complex linear group and also the twice dimensional real rotational group, then that means that O of gamma has to be an element of GLM comma C intersection with O of 2M, right? That's the only way that this is possible, is that it's the element of both of them. It means that it must be in the intersection. And so the intersection of this is precisely equal to U of M. And that completes the proof. Since this is any element of Hall of M, that implies, sorry, there's not a lot of space here. Let me make this a little smaller. Yeah, let's give us a little bit more space. So the niceness of digital editing, Hall of M must be equal to U of order M. And that completes the proof. I hope it's clear what we did here. Part of this might be unsatisfying if you are not aware of the isometry group of the metric, but you can think of it like this. It's a Riemannian manifolds are real, and what preserves the metric are transformations that preserve distances, right? Because that's what the metric measures. And so the group that preserves the real group that preserves distances is the orthogonal group, and the orthogonal group on it wouldn't be on M, it would be on 2M, because M is our complex dimension, so we have to translate that to our real dimensions, which is 2M. That is how we got here. And so then we said that O of gamma has to be an element of both of these groups, which means it has to be an element of the intersection, and therefore it must be an element of the unitary group on of order M, which is our complex dimensions. That's how we order the unitary group. So I hope that's clear. So this is the proof that our holonomy on a Kähler manifold becomes this simple, simpler group. The group of rotations, or the group of transformations on a complex space that preserves its complex modulus, or preserves the complex modulus of its elements, and in this case the vectors. So with that consequence out of the way, let's now look at the third one, the third definition of a Kähler manifold. Again, we start with a Hermitian manifold. Hermitian manifold M H yeah, M and H and J, and we this time what we're going to do is we're going to define in local holomorphic coordinates, which we are guaranteed because we are on a complex manifold. Coordinates, let's call them Zj, where j is equal to 1 to m, and if H agrees with the Euclidean metric, then on CM to the first order, and I'm going to explain how I mean this in a little bit. So that means that HJK, each of the components in this local coordinate, is equal to delta JK, which is the Euclidean metric, plus O of mod z squared, or the length of z squared, then M is a Kähler manifold. Oops, Kähler manifold. So this is the third definition, is that the Hermitian metric has to be locally flat. So we sometimes call this the local flatness condition. There's no long proof with this version of the definition of the Kähler manifold. We've already kind of come up to it. What we're saying is that the Kähler manifold has this local flatness condition. So we can see this like if M was only Riemannian, not symplectic, then we would have GJK equals delta JK plus or O of mod x square, the real coordinate. And if M was only symplectic and not Riemannian, then we know from Darboux's theorem that omega would be equal to dxj wedge dyj, sum over j, right? But on a complex, and if M is complex, only complex, then we will always find holomorphic coordinates. Zk equals xk plus I yk, right? So these three facts are independently true if we can guarantee one of these properties. The interesting thing about Kähler manifolds is that this definition implies, so this is not a long proof, I was saying, it's not a long proof, it's just a corollary, is that we can always find coordinates, where all three are simultaneously true. And this is a very powerful fact, right? We can always find holomorphic coordinates where the metric is flat to the first order, and the symplectic form is this simple wedge of all of the coordinate covectors, or coordinate one forms. So this is a very powerful statement, and it's only ensured on a Kähler manifold. And in fact, if we can do this everywhere, then that is what signals to us that what we're working on is definitely a Kähler manifold. So this is true if and only if we're on a Kähler manifold. So that's the significance of definition number 3. So now on to definition number 4. So the last definition of the Kähler manifold that we're going to look at is, again, let's start with a Hermitian manifold. We're always going to need a Hermitian manifold. It's just we can find different ways of turning it into a symplectic manifold, I suppose. So I'm not even going to write it. Let's just say MJH. Sorry for swapping J and H all the time, but yeah, MJH. And we have a Chern connection. And we impose a Chern connection, nabla C. And so then if the torsion T nabla C of xy is equal to 0, then M is a Kähler manifold. This is the fourth and final definition of a Kähler manifold that we're going to look at. If the Chern connection is torsion free, then we get a Kähler manifold. So let's look into, this time what we're going to do is we're going to look at a proof that this means that the Chern connection becomes the Levi-Civita connection. Okay, so for the proof, let's go to the next page, give ourselves some space. So the proposition is let MJH be a Hermitian manifold. Then if we give it a holomorphic, remember from last time, holomorphic vector bundle, then it'll have a churn connection because every holomorphic vector bundle admits a churn connection. So then if the torsion on that churn connection is 0, then nabla C, oh, I'm putting it at the bottom, nabla C is equal to nabla Levi-Civita, right? So the churn connection is the same thing as the Levi-Civita connection. So let's prove this. Proof. First things first. So what do we know about the Levi-Civita connection? What we know about the Levi-Civita connection is that it has two properties. It has to be metric compatible. One, it has to be metric compatible. And two, it has to be torsion free. Well, torsion free is easy. We just hypothesize that our churn connection is torsion free. So by hypothesis, nabla C is torsion free. So that's all good. So let's look at the metric compatibility. For metric compatibility, we need nabla C of G is equal to 0. But we're on a Hermitian manifold, right? What we have now is the churn connection, which is a Hermitian connection. So nabla C is a Hermitian connection, which means that nabla C is compatible with H. But G, as we saw, the induced Riemannian metric is just the real part of H, right? So therefore, that implies, let's put some separation here, that implies that nabla C of G is equal to 0. So the churn connection is always automatically metric compatible and Riemannian metric compatible. But the thing that will prevent it from being the Levi-Civita connection is whether or not it's torsion free. Therefore, the condition on which the churn connection will be the Levi-Civita connection is its torsion freeness. And we know that the Levi-Civita connection is unique. That's the fundamental, it's part of the fundamental theorem of the Riemannian geometry. So therefore, this churn connection must be the Levi-Civita connection on the Riemannian manifold. So therefore, proved. Nabla C is equal to nabla LC. That's a pretty short and hopefully self-explanatory proof that they are one and the same on a Kähler manifold. And this is one of the hallmarks of a Kähler manifold is that its Levi-Civita connection will be the same as its Chern connection. So now that we have all of these definitions out of the way, it's time to see why these are equivalent. Now, unfortunately, let me write this. Unfortunately, the problem with showing their equivalence is that of the four definitions is that they are it's extremely difficult to prove. It's a very long and technical and heavy proof. I haven't gotten into the whole proof yet. So for the scope of this course, it just seems like out of scope for us to discuss that, but it's necessary to understand that they are in fact equivalent. So let's just give a high-level overview of what makes these conditions equivalent. So let's get into it. Let's first list out all four of the definitions that we have. First of all, d omega is equal to 0, where omega is the Kähler form, or the fundamental form, on the Hermitian manifold. All of them start with the Hermitian manifold, so for all of these, M is a Hermitian manifold. Number two is that the connection on J, or the connection computes with J. This is definition number 2. You could call this the complex structure is parallel condition, if you remember from our parallel transport idea. Number 3 is that in local coordinates, h, j, k bar, I missed the k bar last time I was writing it, but this is because of the sesquilinearity, is equal to delta j k bar plus order of the terms of order z squared, right? And this is what gave us that triple coincidence of these of the coordinates. And number 4, the one we just did, is that the Chern connection, nabla C, so the torsion of nabla C is 0. It's torsion free. Torsion free Chern connection. And we could call this one the local flatness condition. So in fact, these are, we call this one the Kähler condition, right? In fact, these are all the Kähler condition, and they're just disguised in different forms. So Kähler condition, and let's see how each of these translates to the Kähler condition, how we would find that these are all equivalent to each other. So first of all, 1 is equivalent to 2 because nabla j equals 0 is equivalent to d omega equals 0 if j is integrable. Again, the proof for this is out of scope, but yeah, so that's why 1 and 2 are equivalent. 1 and 3 are equivalent also. And so that is because we can find such holomorphic coordinates precisely when d omega equals 0. That's when these coordinates would exist. And number 3, 1 is equivalent to 4 because the torsion T of nabla C is equal to 0 if and only if partial of omega, or the Dolbeault operator on omega, is equal to 0, and the conjugate Dolbeault operator is also equal to 0, which means that d omega equals 0. I know that we're not really explaining a lot of the reasons why these are true, but it's still important, even if we can't cover the proof for these, to understand the structure of why all of these definitions are equivalent. And maybe I will have a link to, I'll add a link to the lecture, the proof for this in the lecture notes. So, but let's look at the structure. So we have definition 1, which is our most fundamental definition. And what we basically said is that there is a structure like this: 2, 3, 4. And so because 1 is equivalent to all of them, we also find that by transitive property, we can find the equivalence between all of the definitions, right? So that's how it works. So because they're all equivalent to the first formulation, they all define a Kähler manifold. That's the idea. Okay, and maybe I'll have a proof of it in the notes. So now that we're done defining the Kähler manifold in as many ways as possible, we are now going to look at some of the extra structures that emerge on Kähler manifolds. Extra structures on Kähler manifolds. My signature not centered titles. So we're going to primarily focus on 3 different structures. We're going to look at the emergence of something called the Kähler potential, which is a function on the manifold. And then we're going to look at special properties of the Christoffel symbols, Christoffel symbols that we looked at in lecture 10. And lastly, we're going to close off with a discussion of something called a Ricci form and the special properties of the Ricci form. So the Ricci form is something that exists on other manifolds, but it's particularly nice on Kähler manifolds. And as you might guess, it's related to the Ricci curvature tensor field. It's just an alternative way to think about the curvature in terms of forms instead of in terms of just a tensor field. So, I mean, we've already been looking at some of the interesting results on the Kähler manifold. We looked at how the holonomy group is the unitary group, and we looked at how the three coordinate Darboux coordinates, the locally flat coordinates, and the holomorphic coordinates coincide for a Kähler manifold. And we looked at the fact that the Levi-Civita connection, if defined on a Kähler manifold, will be the same as its Chern connection. And so we've been looking at a bunch of results for Kähler manifolds already, but those were kind of like immediate consequences of the definition. Now we're going to look at some of its extra structures. So let's start off with the Kähler potential. So the Kähler potential. Kähler potential. In order to discuss the Kähler potential, which is a function that locally exists on every Kähler manifold, we're going to have to state a particular lemma that we're going to prove in the next lecture. It's called the partial bar lemma. The partial bar lemma says that on every Kähler manifold, if if alpha is a differential form, which is partial bar closed, and D exact, then there exists beta such that alpha is equal to partial bar beta. So this ensures the existence of a particular form beta, and that's what we're going to be using in order to conclude the existence of a certain potential. Now let's move on. So we can now define the Kähler potential. So the Kähler potential is, so we're going to say that M is a Kähler manifold. So we have this quadruple M, J, G, omega. So then there will be a function K that is locally defined, U subset of M, that is real valued. This is going to be our Kähler potential. It's going to be defined like this. Take the symplectic form, and K is defined to be I times partial bar of K. Now that's why we needed the partial bar lemma, because the existence of this is ensured. Existence is ensured by partial bar lemma. And because we know that this is partial closed, this is partial bar closed, and D exact, so it satisfies the preconditions. And so if let's say that we have local coordinates zj, j goes to 1, from 1 to m. In these coordinates, we can rewrite this as omega is equal to I times partial square k. So this is going to be a double derivative partial zj partial z bar k dzj wedge dz bar k. This is it. And so this would be, let me put that in a color. This is omega j k bar. And if we remember that omega xy is equal to gj xy, which so omega j k bar is equal to I g j k bar. That implies that g j k bar, the Riemannian metric, is equal to partial square k gz j partial gz bar k. And this is called the Kähler metric. It's a specific refinement of the normal Riemannian metric. Okay, so one thing to note about the Kähler metric is that it's locally defined. Locally defined. As we established before, the way we form a Kähler potential that is defined over the whole manifold is we do another local to global patching. Local to global patching. This is a theme in our whole series of local to global patching. We take the Kähler potential on all of the individual local patches, and then we patch them together to get a global Kähler potential. That's how we define this potential on the whole of the manifold. Because the partial bar lemma is only true on a Kähler manifold, this potential is also only guaranteed to exist on a Kähler manifold. One last thing that I would like to talk about with regards to Kähler potentials, let's go to the next page to talk about these, are Kähler transformations. Let's center that a little bit. Kähler transformations. So the idea behind Kähler transformations are that they are transformations that preserve the Kähler metric, right? So since it's a double derivative, the Kähler transformation is immune to first order changes in the coordinates. So let's call our Kähler transformation kappa. I write kappa kind of like this to differentiate it from k. It goes from C infinity functions on U to C infinity functions on U, right? And so it's a map. The way it will map is it will take a function k of zj, zk bar, or z bar k, to k of zj, z bar k, plus f of zj plus f bar of z bar k. That's a Kähler transformation. So this is kappa. So what we're trying to say is that, remember we were trying to do this local to global patching on the overlaps. So on the overlaps between U alpha and let's say U beta, our favorite two, here what we require is k alpha is equal to some kappa of k beta, where kappa is a Kähler transformation. So it preserves the Kähler metric. So that's what we mean when we want to, when we say local to global patching. The niceness condition or the compatibility condition is this. And that's how we obtain a global Kähler potential. Global Kähler potential. So the thing is that in on a Kähler manifold, if it's compact, then we can define a Kähler potential globally. But if it's non-compact, we're not ensured the existence of a global Kähler potential, and so we can still make a global Kähler potential by patching together local Kähler potentials using this compatibility condition. So now that we're done with Kähler potentials, we're going to move on to the structure of the Christoffel symbols on a Kähler manifold. So the Christoffel symbol structure, we'll call it the Christoffel structure of Kähler manifolds. Kähler manifolds. The first thing to note, statement number 1, mixed. So we're talking about bottom indices. Remember that gamma has A, B, C, right? These are the components of the Christoffel matrix. It's a three-dimensional matrix. So we're saying that these bottom indices are, so they can either be holomorphic or anti-holomorphic, right? Maybe we haven't addressed this explicitly before, but the non-barred indices are holomorphic and the barred indices are anti-holomorphic. So the only non-vanishing gammas are the homogeneous ones on the bottom indices, meaning either you have gamma A B, or sorry, BC, or you have gamma A B bar C bar. That's what I'm saying. So either both of the bottom indices are holomorphic, so they transform according to the holomorphic tangent space, or they're both anti-holomorphic and they transform with the anti-holomorphic indices with the anti-holomorphic tangent space. So that's the first thing. And because of the fact that all the other Christoffel symbols vanish, and this is because nabla LC of J is equal to 0, that the complex structure is parallel, so the holomorphic and anti-holomorphic directions don't mix, and therefore the connection between the holomorphic and anti-holomorphic directions, which the Christoffel symbols come from the connection form, right? So therefore those are 0, and therefore we can, I'm going to skip the algebra for this, but I'm going to state it out here that the Riemann curvature tensor components are A, B, C, D bar. These are the only non-zero Riemann tensor components, and so these are equal to minus partial z d bar of gamma A, B, C. These are the only non-zero components where D is a barred coordinate and B and C are normal unbarred coordinates. So in order to see where this leads to, like, we can actually refine this formula. And in order to figure that out, we're going to need to figure out what the trace of the Christoffel symbol is. And so we're going to show that proposition, the trace of the Christoffel symbol is, so we're talking about this specific trace. We're doing it in terms of components because if you remember from lecture 9 and 10, the trace is very difficult to express in terms of non-coordinate notation. So we're using the coordinate notation right now. So, which is fine because the Christoffel symbol is a very coordinate dependent object in the first place. It's not a tensor. It's the logarithm of the determinant of hjk. This is the Hermitian metric. So, sorry, I got the indices wrong. KL bar. Yeah, let's not overlap indices. So that is what we're going to try to prove. So proof, this is going to be, we're going to use a pretty famous result here called Jacobi's formula. So let's first state Jacobi's formula. Jacobi's formula. So this is the formula for the derivative, how to expand the derivative of a determinant. Let's see that. Okay, so on one side we have a parameter t, and then we have the derivative of the determinant of a of t. So A is a matrix with a parameter t. This is then equal to the determinant of the matrix A of t multiplied by the trace of this whole expression A of t inverse multiplied by the derivative with respect to the parameter of the matrix itself. So you might see where we're going with this, and so we're going to expand the right hand side. So first of all, let's start with partial zj of ln of determinant of hk l bar. We use chain rule. If we use chain rule, then the derivative of the logarithm is equal to 1 over the argument of the logarithm. So determinant of hk l times partial zj of the determinant of the matrix itself, in which case this is hkl bar. Of course, we should probably put different indices down here because we don't know that they're summed. So pq bar, let's say. Now we use the formula. So let me give myself a little bit more space here. So then we're going to expand this part out. If we expand this part out, what do we get? We get first the determinant of the matrix. In this case, it's hkl bar. So we can call that pq bar again. In fact, we don't need to call it pq bar. Let's call it rs bar, and the point will still remain the same. Because we're taking the determinant, we're summing over all of the indices, right? So these will still cancel each other out. I hope that makes sense. So these will cancel each other out. This will give us 1 times the trace of the inverse, which is, well, let's just call it h pq bar. I'm running out of letters. Let's call it bc bar inverse times the partial derivative of the matrix itself, which we're calling KL bar. And so if we take the trace over this whole thing, and the inverse of this is called HBC bar, right? So then we get HK L bar partial partial ZJ of, yeah, HKL bar. Now there's a sum over this whole thing. So yeah, so Einstein summation convention. So that's the right-hand side. So let's think a little bit about the left-hand side. So for this, we're going to need uh, the original expression for the Christoffel symbol on a Riemannian manifold. Let's recount what that is. Gamma ijk is equal to half, or a Hermitian manifold in this case, h I m bar partial. Let's abbreviate the partials because there are going to be a lot of them. Partial j h k m bar plus partial k. So these are like, this is just a notation for partial partial zk, right? That's what I'm saying here. H j m bar minus partial m h, oh, there's a bar on that, m jk. Now, because we're going to replace these indices, so this will go to I and this will go to j. And so, right, that's what we had. That's what we had over here. So if we do that, then let's replace all the j's first. The j's will become i's. Let's do that in blue. I, I, I. And the k's will become j's. And let's do that in pink. So the k's become j's. K's become j's. And the last k becomes a j. Now, the first and the third term here will cancel each other out. And it's a little difficult to see that. Let's write the first and the third term. Half h I m bar partial I h j m bar and half h I m bar partial m bar h I j. How are these the same? They don't look the same. They have different indices. Well, remember from tensor algebra that any summed index can be replaced. So since we can swap actually the indices on this one. So we can swap I and m bar. So let's turn this into m bar and this into I. Then this will become I and this will become m bar. And remember that the Hermitian metric is symmetric, so we can swap these indices now that right. So because this is actually h hat, so so since we're taking into account the barred index, it's going to be symmetric, and so therefore we can turn this into I m bar, and we can turn this into j m bar. And now look, they're the same, right? Now that they're the same, now we can cancel these off. So I hope that makes sense. Index manipulation is a little bit tricky, but hopefully if you work on it yourself, you can figure it out as well. So the last remaining one is this one. So we get half I m bar partial j h I m bar, right? And this is almost what we want. Remember, we have this expression. We're almost there. Let's put this back to its original configuration. We just need to replace the dummy indices, or the summed indices again. And we're going to replace I with k. So if we replace I with k, we get this. And if we replace m bar with l bar, then we get this. Right? And there's an extra half here, and that's because we use the Christoffel symbol for a real manifold. If we use a complex manifold, then we'll have twice the number of real dimensions. So actually there's an extra factor of 2 that we will get. Or let me say it like this. So times 2. So then we get the same thing. Partial partial z j h k l bar. And so therefore, since this is equal to this and the right hand side is also equal to this, therefore we have proven what we wanted to do, which is iij is equal to this whole business here, right? It's equal to partial, let's abbreviate it, partial j of ln of det of hkl. And that proves our proposition. So now let's see how that factors into what we were talking about before. Let me remind you what we found out was, or what we wrote out was that a, b, c, d bar is equal to minus partial z d bar of gamma of a, b, c, right? And so this isn't directly using, I forgot to mention this, so this isn't directly using the gamma iij, right? Because we don't have the summed index, but imagine what we, or like just think about what we would have if we took the Ricci tensor, right? So the Ricci tensor CD bar would just be, or sorry, BD bar probably, right? So would be equal to R A B A D bar, right? This would be equal to minus partial Z D bar of gamma A B A. And gamma A B A, there's a Christoffel symbol identity that these two can be swapped. So this is actually the same thing as AB. And so there we get that same structure. And so then we get minus partial Z D bar of partial Z B of the ln, the natural logarithm of the determinant of h. From this we get that, so this is now a second derivative, right? So let's write it as a second derivative, minus partial square partial z d bar partial z b of the ln of the determinant of h. So this is the BD component of the Ricci tensor now. So that is our result on the Kähler manifold, that the Ricci tensor has this nice form to it. So now we're going to move on to talking about the Ricci form, which will nicely flow from our discussion on the Ricci tensor of the Kähler manifold. So the Ricci form. The Ricci form is a form, an exterior differential form that we will derive from the Ricci curvature tensor. But the problem is that the Ricci curvature tensor, Rich, is symmetric. So the common construction of a form which requires the alternating map would just give us 0. A2 of Rich is 0. So since the second order alternating map of this tensor is 0, how can we construct a form out of the Ricci tensor? We instead employ a different method. What we will do is we will define the Ricci form rho of xy as being defined to be the Ricci form, the Ricci tensor, but with we will first take the j map of the first input. This will turn the Ricci tensor from being symmetric to being antisymmetric. So then we can prove that this is indeed antisymmetric. Let's take rho of yx, but this is equal to, by definition, Ricci of j of x, y. And then we flip it because the Ricci tensor is symmetric, which was exactly the problem we had before. So y, j of x. But then let's use one of the Kähler conditions, which is nabla LC of j is equal to 0. This actually implies that the Ricci tensor is compatible with J because it's built off of the metric. So we know that this is equal to Ricci of xy. So then we can apply another two j's on top of this. So we get j of y, j of x, and so then we get Ricci of j. Sorry, I mixed it up. My bad. Then this should be, yeah, this should be x and this should be j of y. And then this should be j of x, and then this should be j of y. Sorry about that. So then we get j of x, and then obviously we get j squared, which gives us a minus sign. If we take out that minus sign, then we get minus Ricci of j of x y. But Ricci of j of xy is the same format. It's equal to rho of xy. So then we get minus rho of xy, which implies, let me give myself a little bit more room here. Let's rewrite that to not be so cramped, minus rho of xy. But then that implies that rho of yx is equal to minus rho of xy. And so it's antisymmetric. But given that we use this condition, this is only true. This is a version of the Kähler condition. So this is only true on a Kähler manifold. That's the point. We can only do this on a Kähler manifold in general because it's symmetric. We cannot turn it into a form, and we can turn it into a form using this strategy, but only if we have a Kähler manifold, because we require an exterior form to be antisymmetric. So to construct that antisymmetric form, we would need the Kähler condition. So we're in the home stretch now. Just a few things left to talk about. So we can now use our already existing knowledge of like the partial bar lemma to say that, okay, well, let's say we have partial bar of f, then this is equal to partial of, let's expand out the Dolbeault operators. Remember from lecture 8 how these are expanded out. You can look at the lecture notes. D z bar zj, which is equal to, I think I'm using a different convention here. My apologies. The notes are written a lot of time apart. Anyway, so zj, so it's that double bar notation that I'm using here. But this is the same thing. I'm writing the same thing as this. So I'll have that fixed next time. Zj wedge dz dzk dz bar k bar. And so if we use this, so we applied the partial bar, then we applied the partial, right? And once we expand that out, we get this. Yeah, I think there's a square missing here. So once we have this, we can say that since the Ricci form is a 2 form, and so we know that in local coordinates, let's say zj, j equals 1 to m, rho would be equal to I Ricci of jk bar dzj wedge dzk bar, right? And so I'm just expanding out its definition, right? Rho of xy is equal to Ricci of jx y, and this is it in coordinate notation. And so we know what Ricci of jk bar is. So we found in the last section that Ricci of cd bar would be equal to, sorry, Ricci of jk bar would be equal to minus partial z bar k bar partial zj of ln of determinant of g j k bar. the matrix. So, or H, I suppose, H. And since this is true, we find this format here, right? And so we find that, yeah, so if we substitute that here, then we get that, we get this format here, and, right, we get that double partial derivative, and we have this basis of differential forms. So combining that, we get rho is equal to minus I partial square partial z bar k partial zj of ln of det of hj k bar. So and then we get that dz j wedge dz bar k bar. And if we compare this to this over here, then we find that rho is equal to minus I partial bar of this whole thing. And let's just call it ln of det of, we can call it h. And that is our form beta. If you remember, alpha is equal to partial bar beta from the partial bar lemma. And so because we found this, so this means that rho is D-closed, but the partial bar lemma doesn't allow us to say that it's D-exact. Not implies that D-exact. And the reason is that det of hjk bar is not a scalar, or it's not a zero form, right? So it's not a proper zero form, it's a matrix valued. So therefore, we can't say that it's D-exact, but that precisely means that rho is part of a cohomology group, right? It's a closed form that's not exact, so it's part of a cohomology group. And what is this cohomology group? In fact, it's the one that's related to the first Chern form. In fact, on a manifold with a Levi-Civita connection, the trace of F nabla is equal to minus I rho. And because of this, we can write the first Chern class as the class involving the form I over 2 pi trace over F nabla. And if we substitute that, we get I over 2 pi times minus I rho, and the plus I and the minus I cancel out, and we get the rho over 2 pi. So rho with a normalization is the representative of the first Chern class. This is an element of H2 dr of M. It is the DRAM cohomology class of our complex manifold. And so that is the neat thing on Kähler manifolds, is that the first Chern class is equal to this. That is our third and final result for Kähler manifolds. So we actually looked at 6 different results, didn't we? 1, we saw that Hall M is equal to UM. We saw that if there's a Chern connection, that the Chern connection is equal to the Levi-Civita connection. Levi-Civita connection. 3, these are slightly out of order, but we saw that the holomorphic coordinates is equal to the Darboux coordinates, where the symplectic manifold is the simplest Darboux coordinates, or follow the coordinate lines, and also equal to the locally flat coordinates, where the metric is the Euclidean metric to the first order. So we now have seen that there always exists a Kähler potential K, Kähler potential with an H, Kähler potential K, such that omega is equal to I partial bar K, and this induces a Kähler metric. 5, we saw that the Christoffel symbols mean that the Ricci tensor looks like this. Jk bar is equal to minus partial square partial zj partial zk bar and of the logarithm of the determinant of h jk bar. And 6, that well, the existence of this Ricci form, but then also that C1 of E is equal to the cohomology class of the Ricci form over 2 pi. So these are 6 important consequences that we have looked at for Kähler manifolds. So with all of that, we're ready to conclude this lecture. It's been a while. It's been a long time. But let's conclude with a little recap of what we did. I'll keep it super brief because we've been here for a long time. First things first, we did another recap, a special recap of how all the previous lectures fit in. All the previous lectures, or previous topics, let's say, were necessary to talk about this. And in fact, like, we didn't even talk about chief cohomology or invariant polynomials. That I feel like if we had more time, we would probably have talked about even more things I had to skip over. But to talk about Kähler manifolds, Kähler manifold, why am I capitalizing it? Then number 2, we looked at symplectic manifolds, which were manifolds that had this omega, which was a non-degenerate 2 form, antisymmetric 2 form, right? We looked also at the interpretation of area preservation, area preservation, a specific type of area called symplectic area. We used Stokes' theorem for that, and then we looked at 4 different ways to characterize a Kähler manifold. And then we looked at some special consequences of these definitions. I won't recount all of them. We just did that. Consequences of these definitions. Let's go back to the previous page to look at them. We looked at the fact that the holonomy group is the unitary group. We looked at the fact that the Chern connection is the Levi-Civita connection. We looked at the fact that there are 3 coincident local coordinate systems that perfectly align. We looked at the fact that we can define a Kähler potential, and we looked at Kähler transformations. We looked at the fact that the Christoffel symbols have an interesting structure where the mixed Christoffel symbols disappear, which affects the Riemann tensor and the Ricci tensor. And then we use the Ricci tensor to construct a new form called the Ricci form, which is only possible to construct on the Kähler manifold because it requires the Kähler condition to fully be antisymmetric. And then we showed that the first Chern class becomes this simple format where it's equal to the Ricci form over 2 pi. And so that's it for today. Next time, as I've said many times, we're going to look at Hodge decomposition. And so we're going to explain, for one thing, partial-partial bar lemma, but we're going to introduce a bunch of things, the Hodge star operator, the Laplacians, and we're going to look at this interesting thing called the Kähler identities. And these are identities that are true on Kähler manifolds and their consequences. And that's going to be an interesting deep dive into the symmetries of the Kähler manifold, including its Hodge numbers and everything. And so that's going to, this is kind of like the lecture where we're going to look at why we've been saying that the Kähler manifold has all this interesting structure. I mean, we've already been looking at some of the interesting consequences, but yeah, we're going to finish off with that, and then we're going to look at Calabi-Yau manifolds in the next lecture, and that will be the final one. So that's it for today. That was Kähler manifolds. We're finally through it. We talked about so many results on Kähler manifolds, and they were all due to the first 10 lectures that we could even start talking about them. So now that we're through them, now we can talk about Hodge decomposition. So see you next time when we're going to talk about Hodge decomposition. Bye-bye.